Alright, welcome back everybody. In this video we're going to look at some more convergence tests. Alright, the first one we see here, the integral test. If we have a series where a sub n is equal to f of n, we can show that the series either converges or diverges based on whether the integral from lower limit to infinity of the function converges or diverges. Which basically says if we have a series, we can find the corresponding integral, and if we know that that converges, or we can find that that converges, we can show that the series converges. In this case, the corresponding integral to this one would be the integral from 1 to infinity of 1 over x to the 3 halves dx. This converges because it is a p integral with p greater than 1. So the series that corresponds to that also converges. There's a quick little note. This entirely determines the question of convergence or divergence for what are known as p-series. And there you go. We can find any whether any p-series converges or diverges based off of what we already know about their integrals for p integrals. Alright, next, the limit comparison test. If we have two non-negative functions, two positive functions, determining our series, we can take the limit of those two, and if it is a finite non-zero value, c, then they both either converge or they both diverge. So what we would do is we would compare the series we're interested in to a series that we already know whether it converges or diverges, and then they will share convergence-divergence behavior. If we take the limit of the ratio of 2 and we end up with 0, and we know the one in the denominator converges, that means the one in the numerator has to converge as well. If we take the limit of a ratio of 2 and it ends up being infinite, and we know the one in the denominator diverges, then the one in the numerator has to diverge as well. Alright, but usually we will try to force the first situation here. We'll try to come up with something that the limit is going to be some finite non-zero value when we look at the ratio of two things. So let's take a look at what this looks like. We're looking at the sum from 1 to infinity of 2n plus 1 over the quantity n plus 1 quantity squared. If we were to expand that denominator, this is 2n plus 1 over n squared plus 2n plus 1. And the biggest term in both of these, it's n in the numerator and n squared in the denominator. So I'm going to compare this to 1 over n. The limit as n goes to infinity of 2n plus 1 over n plus 1 squared all over 1 over n is going to be equal to 2. Okay, so these two share convergence-divergence behavior. Since the sum from 1 to infinity of 1 over n diverges because it is a p-series with p equal to 1, then the sum from 1 to infinity of 2n plus 1 over the quantity n plus 1 squared also diverges by the limit comparison test. Alright, let's compare the series in part B here. We'll compare it to 1 over 2 to the n. The limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n equals 1. So they share convergence or divergence behavior. Since 1 over 2 to the n converges because it's a geometric series with absolute value of r less than 1, the sum from 1 to infinity of 1 over 2 to the n minus 1 also converges by the direct comparison test. All right, I'm going to compare this to uh, 1 over n squared. Again, I'm just using the largest power of the term in the numerator and denominator of the series that we're trying to show convergence or divergence, taking that ratio, because then when I take this limit, it's going to be a finite non-zero value. And so that limit in this case is going to be 3. All right, and then since the sum from 2 to infinity of 1 over n squared converges because it's a p-series with p greater than 1, then the sum from 2 to infinity of 3n plus 2 over n cubed minus 2n converges by the direct comparison test. Alright, now, example D is unlike any of the other examples we looked at before. It is not just a rational function. So as far as comparisons go, we're not really sure right here what we want to do with this. This is kind of a neat comparison. I'm going to compare this to 1 over n, because then I've got the limit as n goes to infinity of the sine of 1 over n over 1 over n. And now I'm going to introduce another variable here. If m equals 1 over n, comma, this is the limit as m goes to 0 of sine of m over m, which is equal to 1. So they share convergence behavior because we got a finite non-zero value. Since the sum from 1 to infinity of 1 over n diverges because it's a p-series with p equal to 1, then the series we're interested in also diverges by the direct comparison test. Alright, that's the end of the examples from this video. See you guys next time. Have a great rest of your day.